I try to make the videos in this series last about half an hour to 45 minutes, but I don't have complete control over that because I also like to finish having just solved a problem rather than stopping in the middle. And so if I tackle a problem that then turns out to take longer than I expected, it can mean that they go on for a bit longer. So I hope that won't happen this time, but we never know. Just to remind you, I'm working through this book here. Actually, I'm not sure whether I'm going to work through the whole book, but I'm working through chapter 1, problems of which there are 60. And I do, if I get to the end of that, then I certainly intend to move on to problems of a different kind. But whether I should do all the problems in the book, then that would be an absolutely enormous undertaking. So I might just choose some choice topics later on. So for the moment, it's problems that involve invariants of one kind or another. So let us see what the next problem is. I'll better share my screen. Here we go. So I think I got up to 27, no, 28, 29. Okay, so I'm on to question 30. So once I've done this, I will be halfway through, which will be a rather nice milestone to reach. Solve the equation. I do like it when problems come along. You just think you're getting used to, there's some processes described and you want to know whether you can reach a certain destination and so on. So that you can see why that involves invariance. And suddenly it says solve the equation x squared. It seems to have nothing to do with invariance at first glance, but obviously squared minus 3 x squared minus 3x plus 3 plus 3 equals x. Doesn't say anything about x being an integer or anything like that. So what on earth is going on here? I think I want to stare at this for a little while. My my instinct is that if I expand everything out, that will probably not be a very good strategy because I'm kind of losing information. I'm losing the information that I've got this nice x squared minus 3x plus 3 in there. On the other hand, is that nice because there's an x on the other side? Can I argue that something is... Actually, one thing I could do is to see whether I can spot a solution. What happens if I take x to be 0? Then I'll have 9 minus 9 plus 3, which does not make 0, so 0 is not a solution. Another one that's sort of slightly calling out... Well, actually, this is just a y equal this thing, and I've got y squared minus 3y plus 3 needs to equal x. If x equals 3, then I get 3 squared minus... Oh, that's a solution. So the y didn't help too much, but when x equals 3, that lot disappears. So I get 9 minus 9 plus 3 does equal 3. So I've got a quartic. I could just divide out by x minus 3, which is a little bit scary. Or I could try to find another solution, but that's what I still want to understand what on earth has it got to do with invariance. And I suppose actually if so this has still got nothing to do with invariance, but I feel it's tempting to say, to write this, x squared minus 3x plus 3 squared minus 3 x squared minus 3x plus 3, because this factorizes nicely. Then over here I've got x minus 3. So what happens if I factorize this? I get x squared minus 3x plus 3 minus 3 times x squared minus 3x plus 3. So I get x squared minus 3x, x squared minus 3x plus 3. Let me just quickly check what I just said. I think that works because this x squared minus 3x can be written as x squared minus 3x plus 3 minus 3. And if I do that, then I'll get x squared minus 3x, so that's fine. And this, of course, I can write as, with some profit, I think, as that. So I actually get, there I can sort of see that dx minus 3 factor without so much guesswork. So if x doesn't equal 3, then I have the equation x squared minus 3x plus 3 equals 1. Can I spot a solution to that? It doesn't feel very hopeful. So if x is what happens if x is large and negative, then this thing is going to be large and negative, and if x is large and positive, this thing is going to be large and positive. So there's definitely, well, anyway, it's a cubic, yes, so there's definitely going to be another solution. I don't know whether I can actually see what it is. If x equals a third, that looks kind of promising. I have a ninth. No, it's not that promising, actually. What could I... So if I want to get this product to be 1, then I can't have them both being integers unless x equals 1, which I... Does that work? 1 minus 2 plus 3. So 1 minus... If x equals 1, I seem to get 1 times 1. Yeah, because the 3x plus 3, this bit cancels. Okay, so x equals 1 is a solution. Was there a nice way of seeing that? Oh, x cubed minus 3x squared plus 3x minus 1, that's slightly embarrassing, equals 0. So we have x minus 1 cubed equals 0. So the solutions are x equals 1 or x equals 3. But I'm 100% mystified by the connection between this and invariants. I think since I've solved the problem, I'm going to move on rather than trying to work out what on earth was actually going on. Maybe at some point I'll look it up. It's a strange way to reach the halfway mark. Let's see if the next question is a bit more conventional, for this. I'm slightly disappointed though, because it was so nice to have a completely unexpectedly non-invariant seeming question, but then to solve it without using invariants means that the fun that I was expecting to get out of it, I didn't get out of it. Let A1 up to AN be a permutation of 1 to n. If n is odd, then the product P equals A1 minus 1, A2 minus 2, up to AN minus n is even. I think I've seen immediately how to do this, prove this. Now why, okay, I may be wrong about that actually. But sum ai minus I. Let's just see whether this works. I equals 1 to n equals 0 because that's just a permutation. Why am I going to use the fact that n is odd? Oh yes, that's... So in particular, the sum is even. So an even number of ai minus I are odd. But since there's an odd since n is odd, at least one, which is what we had to prove, because this is even if and only if at least one bracket is even. At least one is even. So why did I get that so quickly? Well, I thought, okay, we need just one of these brackets to be even. And there've already been questions on this sheet, so this is an example where doing the sheet, doing the questions has sort of improved my speed, so to speak. When you've got questions about permutations of 1 up to n, then it's often quite useful to look at the sum as an invariant. And so I just sort of wrote this thing down without thinking, really. So let's move swiftly on. 32. Many handshakes are exchanged at a big international congress. What a beautifully timed question. That will not be happening this year. Many handshakes are exchanged at a big international congress. We call a person an odd person plenty of jokes one could make here, but I will resist the temptation. That's supposed to be my italics. If he, not my wording, has exchanged an odd number of handshakes. So I think I would prefer a they in there, but I'm just sticking with my copying out what's actually in the book. Otherwise, and here comes another one, he will be called an even person. Show that at any moment I have a feeling this is going to be very quick as well. There is an even number of odd persons. Well, that's trivial, I'm afraid. If you know the right stuff, which I do. Proof. So I know this is basically the handshake lemma in graph theory. So let's just say let AI be number of times person I shakes hands, then sum of AI, each handshake contributes 2 to the sum of AIs, because there are 2 people involved in a handshake, so equals 2 times number of handshakes. So sigma AI is even, so an even number of AI are odd, which in the language of the question means that there are an even number of odd persons. Okay, so we're getting through a lot of questions, but I'm not having a particularly interesting time. I'm not systematically finding clever invariants. Start with 2 points on a line labelled 0, 1 in that order. It's taking me longer to write the questions out than it is to answer them at the moment. So I'm bound to get caught out and sort of thinking that I'm super quick, and then I'll take 45 minutes on the last question, but well, I hope that won't happen. I'm even going to go with the American spelling. 0, 1 in that order. In one move, you may add or delete. Now that I've started with American spelling, I will continue neighboring without a U to neighboring points 0, 0 or 1, 1. What does that even mean? I'll come back to that in a moment. Your goal is to reach a single pair I have not understood this question at all yet, of points labelled 1, 0 in that order. Can you reach this goal? Oh, I think I do understand now what's going on. So let me just try to explain that. So we have a line like this. We stick a 0 and a 1. And now I can just put in whenever I want 2 points, 1, 1. But I can't put them on either side of this 0 because they have to be neighbouring. So I could put in something like 1, 1. Oh, and I can also delete. And I could put in a 0, 0 sort of over here somewhere. Then I could put in, then if I wanted to, I could remove that pair of consecutive noughts. And so on. And I want to end up with just 1 0. So this looks very much like an invariant question. It looks pretty hard to get to 1 0. So I think there should be some invariant that distinguishes things that distinguishes 1 0 from 0 1. What I'm tempted to do here is count it's sort of to look at not 0 1 but minus 1 1 and sort of sum as I go along. Let me just quickly, so if I start with a 1, let's say 0 becomes 1 and 1 becomes minus 1. Then what happens as I go along here is, I'm not sure where that's getting me actually. Um, it sort of feels as though it might have something to do with bracketing as well. That if when I added 1, 1, I sort of thought of it as an open bracket followed by a closed bracket, then I sort of okay. What could the invariant be that distinguishes 0, 1 from 1, 0? I'm now going to try and be systematic. So I want an invariant of arrangements of noughts and ones down lines. And I want the value of that invariant, if my arrangement of noughts and ones is that, to be different from the value of my invariant if I have 1, 0. So that tells me straight away, if it's a numerical invariant, which it doesn't have to be, of course, it certainly can't be some kind of linear combination of the values, and it can't be something like it can't be a symmetric polynomial a polynomial that just depends on the values I've got there and is symmetric in the values in some way, because 0, 1 is a permutation of 1, 0. So somehow that cuts out a big class of invariants. So it feels as though it's got to depend in some way on the ordering as you go down the line. So I wonder if I just took an alternating sum or something like that. So I just, because that way I start by taking a plus, and then I take a minus, and then that actually, that was rather a nice idea, because when I add, at least when I add 2 1s, nothing changes. And when I add 2 noughts, trivially nothing changes. Slightly anxious about trivially nothing changing when I add the noughts, because that would mean that, oh wait, it's not so trivial, because if I were able to add the noughts, okay, so I like this. So if I've got numbers A1 up to AK going down the line, the invariant I'm going to think about is A1 minus A2 plus A3 and so on. Actually, this will be an even number, minus A2K. I think this has a good chance of working. So is that an invariant? Well, if I just supposing I have, so all these are they're all equal to 0 or 1. If I stick 0, 0 anywhere, what's it going to do? It'll leave the ones beforehand with the same sign that they had before, and it'll leave the ones afterwards with the same signs that they had before, and it will add 0 minus 0, so it won't change anything at all. And if I stick 1, 1 in, it again will shift those by 2, so it won't change the signs I'm associating with them, and it won't change that, and it'll add 1 and subtract 1, so it won't change the thing. But if I start with 0, 1, then I get 0 minus 1, so that's negative, and if I start with 1, 0, I get 1 minus 0, which is positive. Actually, it feels a bit more natural to go minus A1 plus A2, but anyway, that doesn't matter. So we've done it. This invariant works. So that was, I feel more satisfied with that, because that was I had a sort of moment of initial puzzlement, then I tried to be systematic, ruling out certain kinds of invariants, realizing it couldn't be symmetrical. Actually, it wasn't quite as systematic as I would have liked. So I sort of came up with the idea of the alternating sum before noticing that that was definitely going to be an invariant. I was thinking more about trying to distinguish between these two. But had I thought I want some linear combination in order such that putting in 2 1s or putting in 2 noughts will not make a difference, I would have been probably led rather quickly to this as well. So it could have been done even more systematically than I did it. But right, so I've been at it for approximately half an hour, but I'm going to take a risk and do one more. Hope that it won't take ages. Is it possible to transform x squared plus 4x plus 3, back to polynomials, into, oh sorry, that was fx equals into gx equals x squared plus 10x plus 9 by a sequence of transformations of the form f of x goes to x squared f 1 over x plus 1, goodness me, or fx goes to x minus 1 squared f of 1 over x minus 1. Okay, that looks pretty scary. But let us, obviously, we know what we're trying to do, and it's easy to see where invariants come in, because when you've got something where you're trying to transform something into something else by means of certain operations, then you're just looking for anything that is invariant under those operations. So that's not mysterious at all. And so what might not change if we do an operations like this? So there's something really quite... So I don't want to start doing what I did with some questions, which was just to sort of do a bit of experiment. Let's try applying these operations a few times and see what happens, because even applying it once seems to be really unpleasant. X squared times 1 over x squared plus 4x plus 3 plus 1. Even if I sort of simplify that, I get some not very nice looking rational function. So I've got to do some thinking. So I've got to see what properties do I notice about these polynomials. I'm wondering whether I can think about roots. So is it going to be the case that when I apply these operations, I will never lose some root that this has, but this doesn't have, or something like that? That seems to be the most promising idea. So this is x plus 3, x plus 1, and this one over here is x plus 9 times x plus 1. So they've both got x plus 1 as a root. Or in other words, they've got minus 1 as a root, x plus 1 as a factor. So my best hope is to try to show that these operations preserve minus 3 as a root, which seems a little bit unlikely. So if I substitute, if f of minus 3 is 0, what is this when I apply it to minus 3? That doesn't look very nice at all. So I get f of 1 over minus 3 plus 1, so that's f of 2/3, and there's no reason that that should be 0. So could it be, because I said we had a rational function, could it be that I've always got minus 3 either on the bottom or on the top? So I've got a rational function that has an odd number of -3s or something involved. Just think a little bit about that. So now I think I'm going to have to take the plunge and actually work out what happens when I apply this transformation, see what the rational function looks like. So x squared, because otherwise I've made a guess based on the roots. That didn't seem to work. And at the moment I'm really struggling to see what kind of invariant I could possibly have. So 1 over x squared plus 4x plus 3 plus 1, which equals x squared times x squared plus 4x plus 4 over, let's put the brackets in a slightly different way, over x squared plus 4x plus 3. So what we do see is that there was a root, as I was saying before, there was a root -3 on the top of this, and now that root appears on the bottom. So at -3, we have a pole of order 1. So could it be that the parity of the order of the pole at -3 is an invariant? I'm not sure I'm going to see why that should be the case, but let's just... Oh, I've made a mistake actually. Instead of taking... I shouldn't have taken x squared. I took 1 over f of x plus 1, so let's get rid of all that. That was absolute nonsense. So f of 1 over x plus 1, so it's actually x squared f of, I'm going to write it differently, x plus 1 over x. And that's actually going to be a bit nicer, because it's actually going to give me a polynomial. I'm going to apply that. So I've been slightly thinking about it in the wrong way. It's a very sort of mistake I might have been expected to make as a child, getting my order of composition of functions wrong. But there we go. So we get x plus 1 squared over x squared multiplied, we get x plus 1 squared plus 4x x plus 1 plus 3 and 3x squared, I mean, which should, because this one originally factorized in a nice way. Oh, in fact, I could have just done it directly. So I just apply, yep, instead of doing what I've just done here, I could apply it to the factorized version and said, but okay, I'll get to the same thing. So it'll be x plus 1 plus 3x, x plus 1 plus x. So that is 4x plus 1 times 2x plus 1. I hope that's right. So it's x plus 1 over x plus 3, x plus 1 over x plus 1. But I'm allowed to multiply both through by bracket, by an x. So I get x plus 1 plus 3x, x plus 1 plus x. Yes, that checks out. So we see straight away that the root minus, well, the roots are now different. The roots of this are -1/4 and -1/2, whereas the roots I had before were -3 and -1. But maybe there's something about these numbers So it looks, I think the invariant is going to be something connected with the roots probably. But while we're at it, let's have a think about what happens to this. So when I apply it to, actually I'm going to write something slightly more general. So x plus a, I'm going to make a guess that it's always going to be a nice factorization. In fact, it seems as though it definitely will. X plus a, x plus b goes to, let's be a little bit careful about this. Well, it's x plus 1 over x plus a, which I will write as x plus 1 plus ax, x plus 1 plus bx. So that tells me that the pair AB goes to, so that's the pair of minus the roots, let's say, goes to the pair, so that's a plus 1x, and then I got a 1, so it'd be 1 over a plus 1, 1 over b plus 1. That's one operation. So what I'm saying, the roots here are minus a and minus b, and if you calculate it, the roots here are minus 1 over a plus 1 and minus 1 over b plus 1. We see that there. Minus 3 goes to minus 1 over 4. So now let's try and do a similar exercise with the other operation. So it's x plus a, x plus b goes to, now it was x minus 1 squared times f of 1 over x minus 1. So f of 1 over x minus 1 is 1 over x minus 1 plus a, but I get to multiply by an x minus 1. So 1 plus a x minus 1, 1 plus b x minus 1. So just again, what did I do? If I apply f to 1 over x minus 1, I'll get 1 over x minus 1 plus a and 1 over x minus 1 plus b. If I multiply both brackets by an x minus 1, that turns into 1 plus ax minus 1, 1 plus bx minus 1. And let's just rewrite that. Equals ax plus 1 minus a and bx plus 1 minus b. And so a, b in this case goes to 1 over a minus 1, or 1 minus a over a. I don't know which is a nicer way of writing it. Let's do it this way, 1 minus a over a, 1 minus b over b. So I'm allowed to apply a composition of these operations, but they look awfully like operations that are well known to form a group of order 6 or something like that, or to generate a group of order 6. But unfortunately, I can't quite remember the details. I think that they cleverly permute 0, 1 and infinity or something. Let's just check that. If I put infinity, I get 0. If I put 1, I get... okay, it looks as though the way I've done it should be permute 0, 1 and minus infinity. So if I put in infinity, I'll get 0. So 0, minus 1 and infinity. I mean, so if I put in infinity, I'll get 0. If I put in minus 1, I'll get infinity. And if I put in 0, I'll get 1. Ugh. So up to signs, it's good. But I think there may be only a finite number of potential things I can get out of this minus 3. Let's just think, if I do 1 over a plus 1 again, so 1 over a plus 1 plus 1 equals a plus 1 over a plus 2. which is a bit troubling. So maybe it's not the group I think it is. So 1 over a plus 1 over a plus 2 plus 1 equals a plus 2 over 2a plus 3, I think. So it's not looking as though it stabilizes in any nice way. And I haven't even thought about the 1 minus a over a. So what can I do at this point? I just want to find an invariant. So what might the invariant be like? Let's try and again be systematic. I want something that doesn't change when I replace a number a by 1 over a plus 1. And that is a little bit mysterious. And it also doesn't change when I replace it by 1 minus 1 over a. So 1 over a plus 1, let's write it in a new place. Sort of some function of a is the sort of lambda of 1 over a plus 1 equals lambda of 1 over a minus 1 equals lambda of a, and also that lambda of 1 does not equal sorry, lambda of 3 does not equal lambda of 9. I'm going to, I think it may help me to look at this if I just write a as a fraction. So what is 1 over m over n plus 1? It's n, ooh, this is looking promising, over m plus n. And what is 1 over a minus 1? If I write, if a is m over n, I get n over m minus 1 equals n minus m over m. And these operations should jump out at me, as they do, or should jump out at one because they're preserving the highest common factor of these, of n and m. But that's, alas, that's not quite there yet, because when I started with a 3, then 3 is 3 over 1. And in fact, I can write the fraction in its lowest terms, and so preserving the highest common factor doesn't seem to be super helpful. So it must be something about the pair of numbers. But, so I could ask the following. So actually, the fact that it preserves the highest common factor is still quite useful. So I can ask, can I get from 1, 3 to 1, 9 if I'm allowed to use operations of the form mn goes to n m plus n, or mn goes to n minus m m. So is there something that's invariant that will distinguish between 1, 3 and 1, 9? It's invariant under these operations. Now, it's not the highest common factor. We know that because these two pairs have the same highest common factor. But so what else could it possibly be? Why can't I just get from 1, 3 to 1, 9? In fact, I'm just going to try to get from 1, 3 to 1, 9 to get some insight into that. So here's what we're allowed to do. So I've transformed the problem, I think. Not quite transformed the problem because I've got two routes to worry about, but I think if I understand why I can't get from here to here, that would tell me that I had to transform the 1 into 1, 1 into 1, 9 or something like that, and maybe that's also impossible. So 1, 3, let's just swap them round and do this, so that gets me to 3m plus n, which is 4. Second one under sum. I want to, let me swap them around, and so 4, 7. If I do n minus m, that gets me to 3, 4. I hadn't spotted that, but it seems that these two are inverse operations. Let's just check that. If I replace that by the second one minus the first one, I get m, and then put in the first one as the second one, I get back to mn. Okay, so they're inverse operations. So that means that in order to get from 1, 3 to 1, 9 using these operations, I would have to get there either by doing a whole bunch of, I'd have to be able to do it either by doing a bunch of these or by doing a bunch of these, because it cannot be necessary to use a mixture of the two, because if I could have a mixture of the two, I can always cancel out things that are next to each other. So now I've got a potentially much easier question. What's happening when what am I doing to the sum here? I'm adding m to it. No, I'm not. I'm adding n to it. So I'm adding 3 to the sum. And then the second time round, well, I just see what happens. If I'll just carry on this process, but actually you can see that it's pretty hopeless, because if I do this, once I've done it the first time, I'm never going to get the first coordinate to be a 1, because it's just getting bigger and bigger. It's always going to be the second coordinate of the previous one, and the second coordinate is always going to be bigger than the first one. So there's no way of getting it that from that operation repeatedly applied, and presumably it would be just as obvious the other way around. So 1, 3 goes to 3 minus 1, 1, so that's 2, 1. Actually not quite so obvious then. It goes to 1 minus 2, 2, so minus 1, 2, and that'll go to 2 minus minus 1, minus 1, so 3 minus 1. I think there's always going to be a negative number floating around now, but let's just see. So the difference between the two seems to be getting bigger and bigger. What happens to the difference? It started off being n minus m, and then here it became n minus 2m. So once one of them's negative, it's going to start getting bigger and bigger, I think. So let's just do another one of these it's -4, 3, and now I think we're away. Now there's no way of ever getting it to be ever getting a 1 again, because I'm always going to have a positive thing, a pretty big positive thing, and a pretty big negative thing. I'm always going to have a positive thing and a negative thing. That I can, because if it goes negative positive, then I'll have positive negative. So it's also alternate between being negative positive and positive negative, and the bigger of the two is going up each step. So that proves that 1, 3 can't get to 1, 9. If I can also prove that 1, 3 can't get to 1, 1, well, it can't. Just look at this again. Then I'm done. So that was a slightly strange. I think there was an invariant involved there. I mean, it was useful to me to know that the highest common factor is preserved, because that tells me that I can't, in order to get to a fraction that equals a ninth, I can't do it by getting to something like 100 over 900. I can't get the bracket 100, 900 out of this process, because the highest common factor is always 1. So if I miss 1, 9, then I'm doomed. So what were the ideas? I'm actually rather happy about that, because it was not a completely trivial problem, and I think I was reasonably systematic about it. But apart from the silly thing at the beginning where I wrote down wrongly what the new f was. But thinking about factorizing it and doing it in terms of the factorization, thereby reducing the problem to one about operations on the roots, although it's more convenient, I thought, to take minus the roots. So then getting something like this, we have the same operations on each coordinate. So I focused on just 1, showed that I can't convert a 3 into a 1, and I can't convert a 3 into a 9. And then the additional idea of thinking about it as a fraction, I suppose I didn't mention, but it's clear that if you start with a fraction or start with a rational number, then you're always going to have a rational number when you do these sorts of operations. Then that eventually solved the problem. So what I liked about that was that there are quite a few reductions and quite a bit of sort of digging deeper and deeper until one saw what was going on and losing the polynomials far behind and eventually cracking it. So that's one style of problem solving which is satisfying when it works out. So I'll stop there. I'm actually quite pleased with all that. Got through quite a few problems, although, as I said earlier, some of them were not totally satisfying just because they came out a bit too easily. Okay, I'll stop there.